Okay, so in this question we have a function and it's asking us to find the y-intercept of that function. So before I go about to solving this question, I want to revisit what it actually means, like what a y-intercept actually is. So first what I'm going to do is I'm going to draw out a plane. So we know that with any sort of single variable function like this, we know that usually conceptually speaking or visually speaking, this function it's going to be a relationship between x and y. And so what this function, what it'll give you is depending on whatever x is going to be equal to, it's going to give you a corresponding value for y. So that's what makes it a relationship between x and y. And then going back to our plane here, that's why when you graph a function, that's why you end up with like some sort of line or something like that. Um, because it's just a relationship between x and y, telling you like what y is going to be equal to depending on what x is. So in this specific case, it's asking us for the y-intercepts, and so it's asking us where like where along the y-axis, where along the y-axis does this function over here intersect it? So where along this line, and or in other words, where x is going to be equal to 0. So in this specific case, there's two ways you can solve this. You can try graphing this function and then just looking at the graph you come up with and just pointing out the y-intercept that way, but we can also do it mathematically, and that'll give you a more precise answer. So, but first, I'll still graph out this function so that you can still get a visual representation of what's going on. So, uh, generally, if you were to graph this, you'd end up with something that like a curve that looks something like this, maybe like this. Now, from here, with this actually, you know what? No, let me rephrase. I'm gonna revisit this. I'm gonna revisit this afterwards because it'll make more sense once we have an actual number. So first, let's find the y-intercept mathematically first, or by doing a computation. So since we're trying to figure out where the line crosses the y-axis, that's going to be when x is equal to 0. So in other words, what is y going to be equal to when x is equal to 0? So to find the y-intercept, we can just plug in 0 for x into our function. So we got f of x is going to be equal to 6x minus 5x minus 4. And I'm going to replace this f of x term with a y, so that'll give us directly what y is. So you end up with y is equal to 6x squared minus 5x minus 4. And then I'm going to plug in 0 for each of these x terms, and that's going to give us a y value. So you'd end up with y is equal to 6 times 0 squared minus 5 times 0 minus 4. And then when you simplify this, you end up with y is going to be equal to 0 minus 4, which equals negative 4. Uh, and so with that in mind, we can come up with a coordinate system that tells us that gives us this coordinate of 0 and negative 4. And if you were to put this on our plane here, you'd end up with a point like somewhere around here. So 0 and negative 4. And so this would be our y-intercept. And so now I'm going to go back to the curve that I was drawing earlier. You can see how this curve for the function looks like this, and it intersects the y-axis at 0, negative 4. So with that in mind, the answer to this question would be B. Okay, so in this question, we're given a function and it's asking us to find the end behavior of that function. So what it's basically asking is just what's the general direction of the line for when you were to if you were to graph this function. So it's basically asking like as the line like goes way all the way to the right of the origin and way all the way to the left of the origin, is it going to go up or is it going to go down? And so mathematically speaking, that means what's going to happen as x approaches positive infinity and negative infinity. So I'll draw a graph here to make it easier to explain what I'm talking about. So let's say we have some sort of hypothetical function with a line that goes like this. So let's say we had a function that looks like this, like a parabola or something. As these lines keep going all the way to the right and all the way to the left, you're going to see that they're going to positive infinity because they keep going up and up and up and up. So for this case, as x approaches positive infinity, this would be x and this would be y. So this would be the positive infinity direction, and this would be the negative infinity direction. You can see that in this case, it's gonna go up in both directions. So mathematically speaking, that's going to translate to positive infinity in the y direction as well. So I'll put a positive and a negative infinity here too. So now I'm gonna focus on like what kind of functions generally give you a graph that looks like this parabola, for example. So recall that usually when you have a function that has we recall that if you have a function like let's say f of x is going to be equal to x squared. We know that if you were to graph this, you'd end up with something that looks like this. And the reason that's the case is because of this exponent here, that second power. Now, let's say you had something that looked like this, where we had, I'll put another graph here. Let's say we had another graph that looked like this, where you have like this, something that looks like this. Generally speaking, one common function that looks like that would be f of x is equal to x cubed. Notice how in this case we have a odd power instead of an even power. So the point I'm trying to make here is that the exponents of your functions are going to have a pretty big impact on the direction that your graph goes in whatever super far left or super far right direction. So the general rule of thumb is that odd functions, so functions that have an exponent that's odd, are going to have one side that's going in one direction like this, and another side going in another direction like that. Another thing to keep in mind is that whether the function is positive or negative is also going to have an impact on the direction. So like in this case, let's say we had f of x is equal to negative x squared. Then instead of looking like this, the parabola would end up looking something like this. So the same behavior, but instead of going up, it's going down. And then that also applies here, where if we had f of x is equal to negative x cubed, that's going to flip it and just invert it, basically. So instead of having this red curve, you'd have something that looks like this. So same behavior, just opposite sides. Hopefully that makes sense. So now we can use that information to focus on this function here. It might look a little bit nerve-wracking, but once you kind of have like there's some other things to keep in mind that'll make it, I guess, more bearable. So what I'm gonna do instead is because for this, basically what the point I'm trying to make is that the two most important things that you should focus on for questions like this is the exponents in your function, as well as whether or not it starts with a positive or negative. So whether or not it's positive or negative and the exponents. So we have a 2 here, a 3 here, and a 7 here. So those are going to be our powers. When you add all of those up together, we can basically come up with like an equivalent function that behaves like this by mashing all of these exponents together into one. And so we can come up with like let me write this down here again. So we have f of x is equal to negative 4x squared plus x 3 x minus 5 to the 7th. We can come up with like a similarly behaving function by just adding up all of these exponents together. So when you do that, you end up with 2 plus 3 plus 7. So in our we have our hypothetical function. Let's call it h of x. We'd have like, I don't know, x to the 2 plus 3 plus 7, which is 5 plus 7 is 12. So you'd have x to the 12th power. And now another thing I want to note here is that we have a negative here, as well as this term being positive, as well as this term being positive. So this would end up turning into something where you have a negative times a positive times a positive, which when you multiply all these together, you overall end up with a negative, because a negative times a positive is a negative, so here, and then times another positive, you end up with a negative. So what that means is that overall, this function is going to be a negative function, and its overall power is going to be 12. So in our equivalent hypothetical function, this would end up being our final equivalent hypothetical function. And so going back to the rules that I've established over here, we can use this information to conclude that this hypothetical function, or this function, is going to behave like this case, in this case, because we have a positive power and it's negative. I mean, no, not positive. We have a even power and it's negative. So with that in mind, what that tells us is that as x approaches positive infinity, the line the line for this function is going to continue progressing downwards in this direction, and then in the negative infinity direction, as x approaches negative infinity, it's also going to trend downwards like this. So we can conclude that with this function, as x approaches positive infinity, y is going to uh, also approach negative infinity, and then as x approaches negative infinity, y is also going to approach negative infinity. And then let me also add a plus here to clarify things. So this would be the end behavior of this function over here. So matching that up with the answer choices, that should be whatever one of these matches up with what I wrote here. Let's see, which one is that? Positive infinity. Wait, positive infinity, negative infinity, positive. Okay, yeah. So I think the answer to this is B. Yeah. So the answer to this question should be B. Okay. All right. So a company's daily revenue from its best-selling product sold at a price of P dollars can be modeled by R of P is equal to 100P minus 2P squared. So at what price P should the company sell this product to maximize daily revenue? Okay. So for questions like this, it's important to make sure you have a strong understanding of how graphing functions work, because that's going to be really important here. Because since we know that this function is going to model the revenue, we know that at some point you're going to have a maximum or a maximum or a minimum. So recall that with functions like this, we can see that the highest power in this function is a 2. So we can conclude that we have a quadratic function on our hands. So if you were to graph this, you'd end up with something that looks like this. So we got our xy plane here, and the function would look a little something like this. And the reason why I'm having it go downwards is because we also have a negative here. So let me rewrite this function so to make it make more sense. We have R of P is equal to 100P, or no, yeah, 100P minus 2P squared. I'm going to rewrite this as negative 2P squared plus 100P. So ignoring this term over here, this is the most important term here because it has the highest power, and we know that it's negative, and so that's why you end up with something like this. If that doesn't make sense to you, you can just look at the case of if you were to graph like f of x is equal to negative x squared, like f of x is equal to negative x squared. If you were to graph this, you'd end up with a curve that looks like this as well. So now going back to this graph, visually speaking, you can see how it has a maximum here. So this line is going to top out somewhere around here before going down. This is going to be where revenue is going to be maximized because that's going to be the highest point of the function. And so we need to figure out for what value, assuming that this wasn't a revenue function and this is just an xy function, which value of x would give the highest y value. That's going to give us our answer. And so there's a couple ways to do that. There's a general formula that you can use for that basically tells you where the vertex of a quadratic function is. So we know that it's a quadratic function because like this function, it takes the form of a function that looks like this. So it takes the form of something that looks like AP squared plus BP plus C. You can clearly see how in this case A is going to be equal to negative 2 and B is going to be equal to 100. So we can say that A is going to be equal to negative 2 and B is going to be equal to 100. I'll write some arrows so you can see. So those are the two numbers that A and B is going to correspond to. And so then there's a formula that we can use to find the vertex pretty quickly for quadratic expressions. We know that the vertex of a quadratic expression is going to be equal to P is going to be equal to negative B over 2A. This is a relationship that's going to tell us like what value of P is going to give you the highest value, or like the turning point, because the vertex of a function is basically where the line transitions from going in one direction to going into another. So like where this line transitions from like going up instead and starts going down, that's going to be your vertex. So plugging in the known values that we have for B and A, you end up with P is going to be equal to negative 100 over 2 times negative 2. So this is going to simplify to negative 100 over negative 4, which is going to equal negative 25, which is going to equal 25. And so what this tells us is that this is going to be the price that we want to get the maximum revenue, because visually speaking, when x is going to be equal to 25, you're going to end up here. And so we'd want to sell the product at $25 to get the highest revenue. So the answer to this question would be F. All right, find and simplify the difference quotient f of x plus h minus f of x over h for the function f of x is equal to 3x squared minus 7x plus 15. Okay, this question is going to get very, very messy because we're going to have to plug in x plus h for f of x, and then plug a bunch of stuff into this fraction, and then simplify, expand things, factor things. Well, not expand things, distribute things, all that crap. So I'll just, fair warning, this is going to be a pretty messy question. But other than that, the computation shouldn't be that bad. It's mostly just there's going to be a lot of room for making silly mistakes, and it can screw you over. So first, let's write out what we have. So we want to find f of x plus h minus f of x over h, and we have our function here. So first, let's find what f of x plus h is actually going to be. For that, to find f of x plus h, that's just as simple as substituting x with x plus h. So you'd end up with a function that looks like 3 times x plus h squared minus 7 x plus h plus 15. And then we're going to have to distribute things around and expand it so that we can simplify in the future. So I'm also going to do that as well. So this is going to end up being equal to 3 times x plus h times x plus h minus 7 times x plus h plus 15. And then foiling this term, you end up with 3 times x squared plus xh plus xh plus h squared. And then that's going to simplify to 2xh because you're just combining like terms. So 2xh. And then we can distribute this negative 7 into this x plus h term, so you end up with negative 7x minus 7h plus 15. And then we can also distribute this 3 into this polynomial over here. And so for that, you're going to end up with, we're ultimately going to end up with an expanded form of f of x plus h, where f of x plus h is going to be equal to 3x squared plus 6xh plus 3h squared minus 7x minus 7h plus 15. Now, looking at this term, I don't see any like terms that can be combined, and so this is going to be the expanded form of f of x plus h that we're going to have to work with. So plugging everything that we know back into this fraction over here, we can say that f of x plus h minus f of x over h is going to be equal to 3x squared plus 6xh plus 3h squared minus 7x minus 7h plus 15, all in parentheses, minus f of x. So 3x squared minus 7x plus 15 all over h. Now you can see what I mean by how this is going to get really, really messy. Now we have to deal with these parentheses terms too, so that we can simplify. So first, well, I can actually get rid of the parentheses for the first term. These don't really matter. But for this case, it's going to be a little bit different. You want to make sure that since this is f of x, we have to make sure that we distribute this negative sign across all of the terms here. And so we're going to have to rewrite this as 3x squared plus 6xh plus 3h squared minus 7x minus 7h plus 15 minus 3x squared plus 7x minus 15 all over h. And make sure that you just, and the reason you really want to make sure you distribute this negative sign is because otherwise you're going to make an algebra error and you won't get the proper simplification, and you're just going to be freaking out, just wondering what went wrong. So yeah, so now we've expanded everything, and from here now we can start to combine like terms and cancel things out and find a simplified answer. So first I'm going to let's find like terms and see like if we can cancel some things out. So the first thing I notice, looking at this 3x squared term here, if my laser, there we go. Come on. Yeah, so we have our 3x squared term here, and then we have another one here, this minus 3x squared term here. So those would be like terms. Since it's going to be 3x squared minus 3x squared, those would just go to 0, and so we can cancel these two terms out. Now we have a, there's nothing for 6xh, so I'm just going to leave that. Oh, I see another like term. So we have negative 7x here and 7x here. We can cancel those out because it's just going to be 7x minus 7x. So these terms are also going to go to 0. And then we have a positive 15 and a negative 15 here. So we can combine those together and you'd end up with 15 minus 15. So those would also go to 0. And so after all those cancellations, you should end up with a simplified fraction that looks like 6xh plus 3h minus 7h over h. And now we're in a really good spot now because you can see here that every single one of these individual terms in this fraction has an h attached to it. And so we can use the rules of the distributive property to take out an h and cancel out h's and end up with a more simplified expression. So going back to recall like with the distributive property, similar to how I distributed this negative sign into each one of these terms, we can take out an h and go backwards and end up with an expression that looks like this, where we have h times 6x plus 3 minus 7 all over h. So from here, you can see how this h and this h are isolated, and so we can divide these together. And then from there, those h's are also going to cancel. So then you'd end up with, after all the dust settles, you're going to end up with a simplified expression of 6x plus 3 minus 7. Wait a minute. I forgot. Oh, wait. I made a mistake. This is supposed to be a 3h squared. And so you'd end up with 3h in here. My bad. So yeah, so the simplified version of this expression would ultimately be equal to this. So 6x plus 3h minus 7. And so matching that up with the answer choices, hold on, my computer is not behaving right now. Yeah, matching that up with the answer choices, the answer to this question would be C. Uh-oh. Yeah, that's me trying to circle it if my computer will listen to me. Okay, yeah. The answer to this question would be C. Alright, determine the discriminant and the number of real solutions of x squared minus 2x plus 1 is equal to 0. Okay, this question is, well, it's dealing with the discriminant like it says in the problem. But before I go through, I'll quickly do a review of like what the discriminant actually is. And it's a function that's useful for determining how many solutions that a quadratic expression has, or any sort of function. But generally speaking, it's used for a quadratic expression. And it's a general formula that you use using the given number, using the coefficients in your equation here, and it'll give you a parabolic function that will tell you how many real solutions the equation has. So basically, like visually speaking, whatever discriminant equation you come up with, let me put a graph here real quick. Whatever discriminant equation you come up with, the graph will look like some sort of parabola, usually maybe something like this, for example. And notice how this parabola, it intersects with the x-axis at this point and this point. So that, with that in mind, it would tell, the discriminant in this case would tell us that there's two real solutions. And so basically, wherever your discriminant parabola intersects with the x-axis, that's going to tell you how many real solutions you have. Now, if that parabola never intersects the x-axis anywhere, then you don't have any real solutions. So then, with that in mind, then there's the formula for the discriminant, which is as follows, which we know it's going to be b squared minus 4ac. This equation is the thing you see in the quadratic formula under the square root or something. So yeah. So now all we have to do is just figure out what our a, b, and c is going to be. Recall that that's just going to be based off of the general form of a quadratic expression that takes the form of like ax squared plus bx plus c, where you can see in this case a is going to be 1, b is going to be negative 2, and c is going to be 1. So then we can plug that into our values, so I'll write it down. So we have a equals 1, b equals -2, and c equals 1. So plugging that into the formula, you end up with -2 squared minus 4 times 1 times 1. And then when you simplify that, you end up with 4 minus 4, which gives us 0. And so, well, with that in mind, then that narrows down the amount of, excuse me, that narrows down the amount of answer choices we have. So we can get rid of A, B, E, and F. Or no, we got to keep F because it tells us that the discriminant is 0. So we can get rid of A, B, and E because the discriminant in those answers isn't 0. So that's one thing out of the way. So mathematically speaking, going back to what I mentioned over here, where like the amount of times the parabola intersects with the x-axis tells you like how many real solutions you have. If we were to use the formula, the way to figure that out is dependent on what the discriminant is equal to. So if the discriminant, I'll call it D. So if D is greater than 0, then you're going to have 2 solutions. If D is equal to 0, then you're going to have like 1 solution, but like one solution repeated twice. And then in the case of D is less than 0, you're going to have 0 solutions. In this case, you can see that the discriminant ended up being equal to 0, so we have 1 real solution. And so now, if that doesn't make sense to you, you can prove this by plugging this. Using the quadratic formula to find what the actual solutions are. Notice how, like, we're going back to the quadratic formula. Let me write that over here. We know that that's going to be equal to negative b plus or minus the square root of b squared minus 4ac over 2a. And notice how the discriminant is under this radical. So let's say, in this case, we know that the discriminant is going to be 0, right? So if we plug in 0 here, you can see that like when you do your plus or minus step, adding the negative b, it's just going to be the same thing, negative b, because you're adding or subtracting 0. But then in the case of when the discriminant is negative, then you'd be taking the square root of a negative number, which would give you an imaginary number, not a real number. So that's why the discriminant being less than 0 has 0 solutions. And then when it's bigger than 0, you're just taking the square root of just a normal number. So that's why you'd end up with 2 possible solutions. So yeah, so the answer to this question would be C. Oh wait, yeah, it would be C. Alright, compute the average rate of change of the function f of x is equal to 2x cubed on the interval of 2 to 4. So there's 2 ways you can do this. Generally, the more general form to solve this would be by using calculus, but there is an easier way to do this. There is a formula that you can just plug numbers into to find the average rate of a change of a function. So we can say that, let's just say r, that's going to be equal to f of b minus f of a over b minus a. And so then all we have to do from here is just plug in the stuff here. So a and b, that's going to be your interval. It's going to be your boundaries. So the lower boundary would be a, so it would be 2 in this case, and then the upper boundary would be 4 in this case, so b going to 4. And so then we have our function f of x here. So let me write that over here. F of x is equal to 2x cubed. So f of b is going to be equal to f of no, I'll start with a. Go in alphabetical order. F of a is equal to f of 2, which is equal to 2 times 2 cubed, which is equal to 2 cubed is 8, and then 8 times 2 is 16, so 16. And then f of b is going to be equal to f of 4, which is equal to 2 times 4 cubed. 4 cubed is 4 times 4 times 4, so 64. And then 64 times 2 is 128, so you end up with 100. That's a bad 8. Let me rewrite that. 128. And then we know that a and b is 2 and 4, so we can just plug it into the expression here. So we can say that we have 128 minus 16 over 4 minus 2, which gives us 128 minus 16 is 112. I forgot how to do basic math. Give me a second. Yeah, wait. 100 yeah, 128 is 110, 18. Yeah, 112. 112 divided by 2. And then 112 divided by 2, that's going to be 56. So the average rate of change of this function would be 56, which the answer would be E. Alright, solve the equation 6x squared minus 5x is equal to 4. Okay, so we have a quadratic expression here. So uh, we can, so because of that, we're going to end up with, assuming that the solutions are real, we're going to end up with two real solutions. And since we're dealing with a quadratic expression, there's two primary ways we can go about solving this. The reason I'm going to say two instead of three is because notice how we have a 6 here. So the leading coefficient of the x squared term isn't 1, so we can't just do a simple factor. We have to do some additional steps or take an alternative approach. But then the other thing I'm going to do is let me also rewrite this expression where everything is on one side, so it looks like a more obvious form. Hold on, let me also full screen this. So this can be rewritten as 6x squared minus 5x minus 4 is equal to 0 by just simply moving this 4 to this side. And so now you can more clearly see that we have an ax squared plus bx plus c kind of thing here, where a is 6, b is negative 5, and c is negative 4. But since the leading coefficient is 6 instead of 1, we're going to have to solve this by either using factoring by grouping or by using the quadratic formula. So I'll show both approaches. I'd say the grouping approach would be more straightforward, but it's a little bit tricky. So if you're not comfortable with it, then I guess the safer approach would just be plugging numbers into the quadratic formula. So first, let's start with, in order to factor by grouping, you need to multiply, the first step you have to do is you need to multiply your a coefficient and your c coefficient. So find a times c, which in this case it's going to be 6 times negative 4, which gives us negative 24. So now, using this product that we came up with, going back to like the way factoring works, where you come up with two numbers that multiply to one thing and add up to another thing, that same principle applies here, except we're going to be using this number instead of c. So we're going to come up with two numbers that multiply to negative 24 and add up to negative 5. And so for that, we can use 3 and negative 8, because 3 times negative 8, that gives you negative 24. And then when you add them together, so I'll show you. So I'll use 3 and negative 8, because 3 times negative 8 equals 24, and 3 minus 8 equals negative 5. So then we can rewrite this expression in a way that looks like this, where we have 6x squared. Oh, and then also I should mention, since we're using factoring by grouping, where basically the reason you want to come up with two numbers that add up to your b term is because we want to split up our b term into two separate things to do our grouping step. So we're going to also have to attach an x to these terms as well. So you'd end up with plus 3x minus 8x minus 4 is equal to 0. And so now we have this expression in such a way where we can take terms out individually and come up with two new terms to find the solutions. So what I mean by that is, first, we can notice how we have a 6x squared and a 3x here. Notice how 6 and 3 are multiples of each other. So we can take out a 3 because we want to take out something that can go into both 3 and 6. You can't put 6 into 3, but you can put 3 into 6. So I'm going to take out a 3 instead. So when you do that, and then also notice how there's an x in both these terms. So we can take an x out of both of them. So we'd have 3x times 2x plus 1. And then going to these two numbers over here, we can do the same thing with 8 and 4. You can put a 4 and an 8, so we can take out a 4. But unlike the previous case, there isn't an x attached to this 4, so we can't take out an x there. We can only take out the number. So you'd end up with just minus 4, and then 4 goes into 8 two times, and then there's an x here, so this would just turn into 2x. And then in order to get negative 4, you just multiply it by 1, so you end up with plus 1. The important thing to note here is notice how we generated a 2x plus 1 term twice. That's what you want, because we're going to merge this and this into one term and just have one 2x plus 1 term. And then we're going to bring these two things together to come up with our other term and set both of those things equal to 0 and then solve for x, and that'll give us our solutions. So factoring by grouping it's just a roundabout way of doing the normal factoring approach, but where you come up with two separate polynomials that are equal to 0 and you solve for x. So when you do that, you should end up with something that looks like 3x minus 4 is equal to 0, and then 2x plus 1 is also equal to 0. solving for x here, you end up with 3x is equal to 4, and so dividing 3 by both sides, you end up with x is going to be equal to 4 over 3. And then in the 2x plus 1 case, this becomes 2x is equal to negative 1. Dividing both sides by 2, you end up with x is equal to negative 1 half. And so these would be the two solutions of this problem. So the answer would be F in this case. Now, if you don't feel comfortable doing that, you could just plug this into the quadratic formula. I guess it's longer, it's longer, but I guess you could say it's the safer approach. So recall that the quadratic formula, that's just going to be negative b plus or minus the square root of b squared minus 4ac over 2a. We know that a is going to be 6, b is going to be negative 5, and c is going to be negative 4, so this would turn into negative 5 plus or minus the square root of negative 5 squared minus 4 times 6, 6 times negative 4 over 2 times 6. So simplifying this, we end up with positive 5 plus or minus 25. 4 times 4 is 16. 16 times 6 is 64, 72. 72 plus 88? Let me hold on. Wait. Hold on. 16 times 6 is 36. 36. Oh, 96. 96. Okay. So 25 plus 96 over 12, which equals 5 plus or minus 96 plus 25 is 11, 9, 11, 12, 121. Okay, so 121 over 12, and then the square root of 121, that's going to be 11. So you end up with 5 plus or minus 11 over 12. And then separating this into two terms, you end up with 16 over 12 and negative 6 over 12. And then when you reduce these fractions, these turn into 4 over 3 and negative 1 half. So honestly, personally, I would much prefer to solve this by grouping, because you can see how, I mean, you could just plug stuff into the quadratic formula, but the math was a little bit intense, and then you'd also have to memorize your common roots, so memorizing that the square root of 121 is 11. So yeah, I mean, either approach works, but you can see how you get the same answer regardless of which approach you take. So yeah, so the answer would be F. Okay, in this question we're given a factor, or hold on, let me scroll up a little bit. We are given a factor f of x is equal to x cubed minus 7x squared minus 14x plus 48 is x minus 2. So what are the real zeros of f? Okay, so what this question is telling us initially is that, well, this is the, well, let's start with what the question is actually asking, where it's basically asking how many possible values for x are there when we set this equation equal to 0. So let me write that over here. F of x is equal to x cubed minus 7x squared minus 14x plus 48, and we have to set this equal to 0. And we need to find how many numbers for x we can come up with to satisfy this and end up with 0 when we plug that number in. But it also tells us that one of the factors is x minus 2. So, hold on, oops, oh man, there we go. So what that tells us is that when this was factored and broken up into smaller terms, one of the terms that they came up with was x minus 2. So we could also say that f of x is going to be equal to x minus 2 times something equal to 0. And so what we're going to have to do is we want to break this up into all of its smallest parts so that we could come up with a bunch of individual equalities that are equal to 0 and solve for x in each of those terms, and that'll give us all of the possible real zeros. Another thing I want to note is, notice how the highest power of the original function is 3. So that's going to tell us, because we're dealing with a cubic function here, that's going to tell us that there's a possibility that there will be up to 3 values for x that we can plug into this that will give us 0. And so when you're doing a problem like this, pay attention to that, because it'll give you an idea of how many terms to look for. Now, notice how I also didn't put anything here. The reason why is because we don't know what that is. We're actually going to have to find out what that is. And in order to do that, we're going to have to use polynomial division, which can get messy really, really quickly, but we'll make it through. So we're gonna have to set up a division thing, so you'd end up with something that looks like where we have to divide this by this. And when you do that, when you take that division, you'll end up with what we want here. So let me set that up here. So we have x cubed minus 7x squared minus 14x plus 48 divided by x minus 2. Now there's going to be three main steps I'm going to focus on for polynomial division because that's how you do it. So it would be divide, multiply, and subtract. These are the three main things you want to focus on, and this will get you to an answer. So now let's start with the division step. So for that, you want to look at your highest power term in the thing you're trying to divide, and then look at this term here, so x. And we want to divide those things together, and that's going to give us our first term that we're going to put here. So you'd end up with x cubed divided by x. That's going to be equal to x to the 3 minus 1, which just equals x squared. So we can put x squared here. So now that we've done that, now we can focus on the, and then also let me move this a little bit. Let me move it over, if it'll let me. Oh, there we go. Yeah. So now we're going to focus on the multiplication step. And so what that entails is with this new term that we just came up with, we're going to multiply it by each of the terms that we're trying to divide with. So we're going to multiply this with this and this. So when you do that, and then we're going to subtract those terms. So now I'm going to set up my subtraction term here. So put a bunch of parentheses and minus here because we want to subtract all of the products that we come up with when we do our multiplication step. So starting with x, so multiplying this and this, you'll end up with just x cubed. So you end up with x cubed here. Then multiplying x squared with negative 2, you'll end up with negative 2x squared. So you'd end up with something like this. Now, after that, that's all of the multiplication that we can do because these are the only terms we had that we could work with. So we can't really do anything with these, so we're going to have to bring those down and work on those later. So now we can carry on with our initial subtraction step. So subtracting x cubed with x cubed end up with 0. And then negative 7x squared minus 2x squared. But there's also a negative here, so it's actually going to turn into a positive. So this is going to turn into minus 5x squared. Then we can bring these two terms down, so you end up with minus 14x plus 48. And then now we just rinse and repeat and do the same divide, multiply, subtract steps that we just did. So doing the same thing, focusing on this term x squared, divide it by x, and you should end up with negative 5x squared divided by x, which equals negative 5x to the 2 minus 1, which equals negative 5x. And that's going to be our term that we're going to put here. Then we set up our subtraction parentheses and put in our negative 5x squared here. And then we can do our multiplication. So we can multiply this with this and this. So negative 5x times x, that's going to give you negative 5x squared, which I put over here. And then negative 5x times negative 2, that's going to give you positive 10x. So we can put that here. Now we can't do anything with the 48, so we'd also have to bring that down. During our subtraction step, this is going to turn into a positive because of the double negative, so this goes to 0. And then this is going to turn into a negative. So, excuse me. And then the sign will flip. So yeah, so negative 5x, or yeah, 10x, so you end up with negative 24x. Then moving down the 48, you end up with this, so negative 24x plus 48. And so we still have some stuff that we can work with. We still have terms here. So we're going to keep going. Basically, you want to keep going until you end up where you can't divide any further or you end up with a bunch of zeros. Ideally, a bunch of zeros, because if you don't end up with a bunch of zeros, that means you have a remainder and you'd have a really ugly function. I don't think the math department would be evil enough to do that on an exam, though, because that would be really time-consuming. So I'm just going to hope that this goes to 0. So yeah, so rinse and repeat the same steps, divide. This time we have a negative 24 here, so we're going to divide that. So you end up with negative 24x divided by x. These x's are going to cancel and you'll end up with negative 24. And then we put that over here, so we have our minus 24 term here. Then set up our subtraction term. Multiply what we have, so negative 24 times x, that gives us negative 24x. And then negative 24 times negative 2 is going to give you positive 48. So then you can see clearly how everything is actually going to go to 0 here. So everything is going to cancel, end up with just 0 plus 0 because of sign flippages that are going on and stuff. So that's good. That's good. So now that we've gotten to 0, there's no more stuff that we can do. We have fully divided this as much as we can, and so this is going to be the final term that we end up with. And that's the term, this is the term that's going to go into here. So now we can move this down. So let me move this down over here. Now we can say that f of x is going to be equal to x minus 2 times x squared minus 5x minus 24. So, and then set that equal to 0. Now this is much easier to work with. You can see how we have a much more simple quadratic expression here that is pretty easily factorable. We don't have to do any other extra crap to split that up. We can just factor that. And then from there we'll have our individual terms. So let's start with that. So, and well, if you don't want to factor, you can also, well, yeah, we're gonna have to factor this. Yeah, we're gonna have to factor this. So then, yeah, from there, let's figure out how to do that. So in order to do that, we'd have to come up with two terms that multiply to negative 24 and add up to negative 5. So two terms that come to mind to me would be 3 and negative 8, because 3 times negative 8 equals 24, and 3 minus 8 equals negative 5. So, yeah. So then we can split that up, and you end up with f of x is going to be equal to x minus 2 times x plus 3 times x minus 8 is equal to 0. The cool thing is you can clearly see how these are the smallest terms that we can come up with, and so we can just set up 3 different equations, set equal to 0, and then solve for x. So we can say that x minus 2 is equal to 0, x plus 3 is equal to 0, and x minus 8 is equal to 0 as well. And that's simple. You just end up with x is equal to 2, x is equal to negative 3, and x is equal to 8. And so these would be the 3 possible x zeros of f that we'd have. So zooming out a little bit, this would be our answer. So if you plug any of these 3 x's into our original equation here, you'll end up with 0, hence why those would be the zeros. So matching that up with our answer choices here, the answer would be E. Okay, we're given a function, and it's asking us to select true statements related to it, pertaining to what kind of discontinuities that you could potentially have. I know this because, well, if you look at the answer choices, there's a bunch of stuff related to asymptotes and holes and stuff like that. So right off the bat, there's one type of discontinuity that we can point out. This is going to have a horizontal asymptote. The reason I know this is because I'm going to focus on the highest power in both the numerator and denominator. Those are very important when you're dealing with rational expressions, because generally speaking, when you're dealing with rational expressions, the highest power of your rational expression is going to have the biggest impact on the way the function behaves in the grand scheme of things, like in the long term. So in this case, you can see the highest power of the numerator is going to be 2, and the highest power of the denominator is also going to be 2. And generally speaking, a rule of thumb for horizontal asymptotes is when the power of the numerator is less than or equal to the power of the denominator, then you're going to end up with a horizontal asymptote. A slant asymptote, that only occurs in a very specific case where the power of the denominator is exactly 1 higher than the numerator's power, so n plus 1, which we don't have here. You can see that both in the numerator and denominator we have a 2. So that's going to give us the case of a horizontal asymptote. So I'll just put HA here, and then slant asymptote here. And then now the difference between the less than versus the equal to case would be where that horizontal asymptote is actually going to be. So in the case of when the numerator power is exactly equal to the denominator power, your horizontal asymptote is just going to be a ratio between your leading coefficients of your fraction. So in this case, 3 and 2. So in this case, the horizontal asymptote would be y is equal to 3 over 2. Now, if it was a case where n was less than d, then it would just be along the x-axis, so y is equal to 0. But yeah, so in this case, the horizontal asymptote is going to be at 3 over 2, but that's besides the point. What matters is that we do, in fact, have a horizontal asymptote. So I'll just check that off over here. Horizontal check. Now we have to look for other forms of discontinuities. So in order to do that, we're going to have to break this fraction up into smaller individual bits so that we can analyze those bits one by one to look for certain things. So let me rewrite f of x over here. So we have f of x is equal to 3x squared plus 21x minus 90 over 2x squared minus 20x plus 42. So we can take out a leading coefficient here. We have a 3 and a 2. And you can see how 21 and 90 are conveniently nice multiples of 3. So we can take that out and end up with 3 times x squared plus 7x minus 30 divided by 2 times x squared minus 10x plus 21. Because the denominator also conveniently had terms that were nice multiples of 2. So now you can more clearly see that this is pretty nice and easily factorable. So we can factor this into 3 times x minus 3 times x plus 10. I use these values because if you multiply them together, you'll get negative 30, and if you add them together, you'll get 7. So you'll be able to factor with those numbers. Then we can do the same thing using the same logic with the bottom. We'd have x minus 3 and x minus 7. And so now we have everything that we need to look for discontinuities. When looking for discontinuities in a rational expression, one of the biggest things you want to look for is parts in your denominator, specifically this x minus 3 thing and this x minus 7 thing, because those are situations where if you look at them, those are cases where you'll end up where the denominator is going to be equal to 0 depending on what x is equal to. So you can clearly see here, let's say we plugged in 3 for x, then this term would go to 0 and this whole denominator would turn into 0, which would give you a divide by 0 issue. And so you wouldn't have a defined answer at that point. Similarly, you can see that here in x minus 7. If you plug in 7, the denominator once again is going to go to 0, giving you a divide by 0 issue. So basically, just look for terms that will give you a divide by 0 issue if you plug in x for them. So, but now there is a difference between like what kind of discontinuity you could end up with, and that's where the numerator comes into play. Basically, if you have a situation, you want to look for terms in the numerator that can cancel out your divide by 0 issue term. And in this case, you can see we have an x minus 3 up here. So in that case, when you have a divide by 0 thing in your denominator that can be canceled out by that same term in the numerator, that's going to give you a whole. And I'll explain why. So let's isolate that for a second. Let's say the fraction was just x minus 3 divided by x minus 3. If you plugged in 0 into this fraction, if you plugged in 3 into this fraction, you just end up with 3 minus 3 over 3 minus 3, right? And then this would just give you 0 over 0, which is undefined. But if you plug in anything else besides 3 in, you're going to get the same number no matter what. You're always going to get 1. And so you're going to end up with a graph that looks like this, where you're going to have a red line at y is equal to 1, except when x is equal to 3. Then you're going to have a hole here, like so. And so, or no, wait, no, that's wrong. That's wrong. That's not a good way to look at it. Or, well, no, you just end up with 1 because you're just dividing by the same thing. So yeah, so you just end up with a graph that looks like this, like I said. So at y is equal to 1 with a line that goes, well, that's not accurate. That's not where it's supposed to go. Like a line here with a hole right there. But you can clearly see how after you hit x is equal to 3, it clearly just continues along the same trajectory as if nothing happened. The difference is with an asymptote, that's not guaranteed to happen. With an asymptote, what happens is you basically have a term that blows up right before the point where the asymptote is without ever actually touching the asymptote. So what I mean by that is, like, generally speaking, a graph that has an asymptote is going to look something like this, where you can see how this red line is just going to keep going up and up and up and just blowing up, and then your asymptote is going to be here. But it's never actually going to touch this asymptote. But it might continue like somewhere else, like it could continue like this. But even this line, once again, is blowing up, but it's never actually going to touch here. But you can see how it doesn't continue along the same trajectory as if nothing happened, like in the whole case. It's a much more erratic behavior of like just blowing up and stuff without ever touching a bar. So that's the difference between a hole and an asymptote. So when you don't have the case where, so when you have a hole, it's going to be this case where you have something in the numerator that cancels out the divide by 0 thing in the denominator. Otherwise, whatever divide by 0 term you have, that's just going to give you a vertical asymptote. So in this case, x minus 7, x minus 7 is going to be a vertical asymptote. So we have a hole at x is equal to 3 and a vertical asymptote at x is equal to 7. And so in total, we have three different types of discontinuities. We have a horizontal asymptote, a hole, and a vertical asymptote. And so matching that up with the answer choices here, the answer would be F. Yeah. Okay. Find the find the range of the given function here. Okay, so before we go through that, I'm gonna quickly compare this to what a domain is. So you know how with a, like, if let's say we have some sort of function that's graphed here, and it goes from like maybe like here to here or something. The domain is going to be basically where along the x-axis your function is going to be defined. So which values of x could you plug into this function and still end up somewhere on this line? So the domain would end up being somewhere between here and here. The range, on the other hand, pertains to the y-axis. So basically, where along the y-axis could you end up on this line? And so that's what we're going to be focusing on for this question. So erasing this real quick, I'm gonna give a quick sketch of what this graph would look like. The most important thing to note here is notice that the leading coefficient here with the highest power is positive. It's a positive x squared. So that tells us that since we're dealing with a quadratic expression, that we're going to have a parabola that points upward. So some sort of, I'm not going to be like exact of what it's going to look like, but it's going to look something like this, where we have like a parabola pointing upwards. And so since we're dealing with a parabola, the range is going to basically be from wherever this is to infinity, so all the way up, because this parabola is going to keep getting bigger and bigger if we go like in either direction, but it'll never go below the vertex, which is here. You can see the vertex is because that's going to be where the line goes from, like, it changes direction. So like right now it's going down, but then at the vertex it's going to change and then start to go up. So basically, in order to find the range, all we have to do is find the lower boundary, so where the parabola bottoms out. That's going to be the bottom, and then the top boundary is going to be infinity, since we're dealing with a parabola. And it also doesn't give us any other conditions, so that's how I know that. You can also kind of see it in the answer choices here, how, like, especially in answer choice B and D, the upper boundary is infinity in both of them, but it has a lower boundary here. So all we have to do basically is just find where this vertex is. And in order to do that, we can use a formula where we can say that x is going to be equal to negative b over 2a. And so at this point, all we'd have to do is find what b and a are. So recall that with a quadratic expression, the formula, it takes the form of like ax squared plus bx plus c. So in this case, a is going to be 4. I mean, no, a is going to be 1, and b is going to be 4. So with that in mind, we can say that x is going to be equal to negative 4 over 2. Wait a minute. Oh, never mind. My bad. I thought my computer was acting up again. But yeah, so now we have this. So yeah, so plugging in a, we have 1 here. So negative 4 divided by 2 gives us negative 2. Here's the caveat though. Since we're dealing with a range instead of a domain, we can't just like use this value as a boundary and then plug in infinity. The reason why is because this function is in terms of x. It's in terms of x and it's not in terms of y. But since we're trying to figure out the behavior along the y-axis, we're going to need to figure out what the corresponding y value is depending on when we plug this in for x. That's going to give us the lower boundary of the range. If this is a domain, then we wouldn't have to do that. Because like this x, this is because you can see here, this is an x value, not a y value. We want a y value. So let's plug that back in so we can find f of negative 2. That's going to give us negative 2 squared plus 4 times negative 2 minus 12. In fact, going further on what I'm talking about, you can even see how B is actually going to be a bait answer, because it's tricking you into thinking you can just use this as a lower boundary, but we can't do that. So simplifying this, you end up with 4 minus 8 minus 12. That should give you negative 16. So, all right, let me clean this up a little bit. That's not a 6. Okay, there we go. Yeah, so this is actually going to be the lower boundary. This is going to be the lower part of our range here. And now, since we're dealing with a parabola, the vertex, it's going to be inclusive, because we know for a fact that this is going to be defined when x is equal to negative 2. Like we know that it is actually in fact defined at 16. I mean at negative 16. If it wasn't defined, then we wouldn't include it. The reason that's important is because square brackets means that you're going to include it, whereas parentheses means you're going to exclude the boundary. But in this case, we're going to include it. So the range is going to end up being -16 to infinity. So now, being more precise with this graph, it's going to look a little more something like this going down here, where the vertex is here at y is equal to -16. So the answer to this question would be D. Okay, find the horizontal asymptote of the graph of the function given here. So recall that with a horizontal asymptote, you're going to have a horizontal asymptote. It's heavily that behavior is heavily dependent on the highest power of the terms in your numerator and denominator. So so in this case, you can see how the numerator has the highest power of 3, and the denominator has a highest power of 2, because generally speaking, that highest power is going to have the biggest impact on the way the function behaves in the grand scheme of things, like in the long term. And so a rule of thumb with horizontal asymptotes is that you're going to have a horizontal asymptote when the numerator, so the highest power of the numerator, is less than or equal to the highest power of the denominator. And then otherwise there is no horizontal asymptote. And so in this case, but then there's another difference where between the n is less than d case and the n is equal to d case. So this is the condition we need for horizontal asymptotes, and then these two conditions that I've written over here is going to determine where that horizontal asymptote actually is. So when the highest power of the numerator is less than the denominator, the horizontal asymptote is going to be at y is equal to 0. In the case of when the numerator power is equal, it's going to be a ratio between the leading coefficients of your fraction. So in this case, the leading coefficient here would be 1, because it's just x squared, and then the leading coefficient here would be 3. So if you had a horizontal asymptote here, then the horizontal asymptote would be at y is equal to, no, that's a 3. It would be equal to the case of y is equal to 3. But one thing to note here, I mentioned how there is no horizontal asymptote when the highest power of the numerator is greater than the highest power of the denominator, but that doesn't mean that there isn't an asymptote. In that there is a very specific case for when slant asymptotes occur. That occurs when the highest power of the numerator is 1 higher than the highest power of the denominator. So we can say that n is actually going to be equal to d plus 1. In that case, you're going to end up with a slant asymptote. So in this case, we're actually going to end up with a slant asymptote because we do in fact have this condition. You can see how the highest power is 3 and the lowest power is 2. And so in this case, you're going to have a slant asymptote, which is not a horizontal asymptote. So in this case, we don't have a horizontal asymptote. So yeah, so the answer to this question would be B. All right, rewrite the given quadratic function in standard form. Okay, that's weird because all of the answer choices here are written in vertex form. So I think what they mean is rewrite this function here, which is written in standard form, in vertex form instead. So let's just do that instead. So we have, so basically what we want to do is, standard form is this, where we have ax squared plus bx plus c, which you can clearly see this resembles that. We want to rewrite this in terms of, vertex form, which looks like this, where you have a times x minus h squared plus k. So we're going to have to figure out what h and k are going to be. And so in order to do that, we're going to have to take some steps of like distributing out stuff and completing the square and things like that. So the first thing I'm going to do is I'm going to take out a 3 from here and here, because you can see how 18 is going to be clearly a multiple of 3. So when you do that, you end up with 3 times x squared minus 6 plus 22. Then we're going to use, or wait, no, there's also supposed to be an x here. Let's put an x here. So x plus 22. Now we're going to use this term to complete the square. And what completing the square entails is you want to find two numbers for that add up to the term attached to your x term here. So two numbers that add up to 6 that are equal to each other. So the easy answer for that would just be 3. So just in this case, it would be 3. And then with that, then you want to square that number to make a third term and basically make like a new quadratic expression that's in standard form like this. And so you'd end up with something that looks like this, where you have 3 times x squared minus 6x plus 9. The problem is, once you do this, this is not equal to this because we added a 9. We added a 9 to get here. So we're going to also have to subtract by 9 as well to basically make a new equivalent expression with a fully new standardized quadratic expression like so. And then we're going to want to factor this, and that's going to give us a new form. The reason we want to factor it is you'll know that you've completed the square properly, where if you factor this, you should end up with 2 of the same terms. So when you factor this, you'll end up with 3 times x minus 3 times x minus 3 minus 9. And then this can be rewritten. This can be rewritten as this, where we have 3 times x minus 3 squared minus 9 plus 22. And then this is going to be an equivalent expression to this as well as this. And all we have to do is just simplify it and we should be done. So we can remove these parentheses or by distributing the 3 back in, so you'd end up with something that looks like 3 times x minus 3 squared minus 27 plus 22. Then simplifying again, you end up with 3 times x minus 3 squared minus 5. So now you can more clearly see that this is going to be k and this is going to be h. And so you can see how we came up with a new function that resembles the form we wanted here. And so matching up with the answer choices, we can say that, well, let's call this f of x. And so matching up with the answer choices here, the answer would be C. All right, we have another function, and it's asking us to find the y-intercept. So that's just going to be basically if you were to graph a function like this and you had like a line that looked like this or something, something like this maybe, then the y-intercept would be here, because you're basically just trying to see where the line or the graph of the function intersects with the y-axis, so the y-intercept. And that's as simple, in order to find the y-intercept, that's just as simple as plugging in 0 for x, and then seeing what y ends up being equal to in that case. The reason it's that simple is because the y-axis, it crosses the x-axis at the origin. So it crosses the x-axis when x is equal to 0, and so that's why you plug in 0. So we'd end up with something that looks like f of 0 is going to be equal to 7 times 0 minus 4 times 0 plus 2 squared, which gives us f of 0 is going to be equal to 7 times negative 4 times 2 squared, which once again will simplify to 7 times negative 4 times 4, which is going to equal negative 28 times 4, which is going to equal negative 112. And so since we use x is equal to 0 to get here, we can come up with a coordinate that's of 0 and negative 112. So this would be the y-intercept of this function. And so the answer to this question would be A. And now let me ignore that. So now we have another problem here, where it's telling us to find all of the vertical asymptotes of the following rational function. What we're gonna have to do for here is we're going to have to break this up into as small pieces as we can and analyze each of the pieces individually, and we can figure out if we have vertical asymptotes on hand. So first, what I'm going to do is I'm going to take out a 5 from the numerator, because we can take that out and end up with something that looks like 5 times x plus 1. And then I'm going to do the same thing on the denominator. We have x squared plus 7x plus 6. Instead I'm going to factor that. And when you do that, you could end up with something that just looks like x plus 1 times x plus 6. And this is going to tell us where our vertical asymptotes are. An asymptote it's a discontinuity, so it's going to be a place where your function is undefined. One thing to note, though, is that it might be easy to say that, oh, we're going to have a vertical asymptote here and here because we have 2 terms in the denominator that could give you a situation where you have a divide by 0 issue, which would give you an undefined answer. But that is wrong, because that's assuming that a vertical asymptote is the only type of discontinuity which you could have, which is not true. There is also the possibility of holes, which in fact we do have a hole here, and I'll explain that, and I'll explain why in a second. So obviously we can point out where our discontinuities are, because we have divide by 0 terms here, where we end up with like x is equal to negative 1 and x is equal to negative 6. The problem is this is the only term that's going to give us a vertical asymptote, and this is going to be a hole. The reason why is because there's also an x plus 1 in the numerator. So basically, when your divide by 0 term in the denominator has a corresponding term in the numerator that can cancel it out, that's going to give you a hole instead of a vertical asymptote. And so as a result, Excuse me. Whoa. As a result, the only vertical asymptote we're gonna have is going to be at x is equal to -6. So the answer would be F instead of A. Now the reason why this is going to give you a whole, let's look at this individually. So we have x plus 1 times x plus 1. Let's say you plugged in -1 into x to get your discontinuity. So you end up with -1 plus 1 divided by -1 plus 1, and then you get your 0 by 0. So yeah, you have your discontinuity, and so, oh, okay, cool. So you might have your asymptote. The problem is, if you were to graph this, this is just going to look like this. The graph for this function, it's just going to be a flat line here at y is equal to 1 with a hole. You're going to have a hole at x is equal to -1. And the reason why, the biggest difference between a hole and an asymptote is how the graph behaves outside of the discontinuity. You can see here how after the discontinuity, it just behaves as if nothing ever happened. Whereas with an asymptote, it would look something like this, where you'd have, I don't know, maybe some weird pointy thing like this or something. That's an asymptote because you can see how like these two lines, they go all the way up into Narnia or whatever without ever actually intersecting with each other. And so it doesn't have that continue as if nothing happened behavior that a hole has, because you just have this flat barrier where the lines will never touch. And so that's the difference between an asymptote and a hole. So that's why the answer is F and not A or D, I guess. So now we have the final question here. So let me get rid of this as well. Sorry about that. Those are just some annotations from when I was running through this exam initially. Choose the function that has the following properties: a vertical asymptote at x is equal to 7 and x is equal to -5, a hole at x is equal to 1, a 0 at x is equal to 3, and a horizontal asymptote when at y is equal to 1. So this question, wow, this is a loaded question. It's really just gauging how well you understand discontinuities and behavior of like rational functions. So let's start with the vertical asymptotes. We know that with a vertical asymptote, you're going to have a vertical asymptote. Let's just say like we have our fraction here. When you have like some sort of like x minus a, x minus b or whatever, like a term in your denominator where you can end up with a situation where you're dividing by 0. One caveat though, your vertical asymptote terms, they can't have the same term in the numerator. So like you can't have an x minus a term here that cancels with it, because if that happens, then you'll end up with a hole instead of a vertical asymptote. So the question wants us to, so starting with the vertical asymptotes, the question wants us to find vertical asymptotes at x is equal to 7 and x is equal to -5. So we're going to need to look for a fraction where we have an x minus 7 term and an x plus 5 term that also doesn't have these terms in the numerator. So let's make sure that those don't exist there. Yeah. So so we don't want those terms. We only want we only want them in the denominator. And so right off the bat, we can eliminate answer choices. B, as well as answer choices. We can also eliminate answer choices D, because and then F as well, because well, none of them have a x minus 7 or x plus 5 term. They have the signs flipped, and then F, it doesn't even have that. It only has them in the numerator. So that's how I know for a fact that those answers wouldn't be the case. Oh yeah, we could also get rid of C as well, because of the fact that it doesn't have these terms in the denominator, which is what we want for a vertical asymptote. Now let's look for the whole case. We want a fraction. We want a term where it says it wants a hole at x is equal to 1. So we want another divide by 0 term in the denominator that's equal to x minus 1, while also having that same term in the numerator. So something like this. This is going to give us a hole because it cancels each other out. And so that's going to give you a hole instead of a vertical asymptote. And so we can see clearly that both answer choices A and E do in fact have that. They do in fact have the whole case because they have they have the canceling out thing that I was talking about here. Now, so we can't eliminate anything. Now let's look for a zero. The zero, you're gonna have a zero whenever you have a situation where basically where you only have basically where you have like a zero term, not a divide by zero term, but like one of these terms, except it's only in the numerator. Because if it's only in the numerator, when you plug in that x value, so let's just say like in this case, a whole at x is equal to 3. So we want like a fraction, like let's have a hypothetical here. We have like, I don't know, 25 or something, and then x minus 3. If we plug in 3 here, we're going to end up with a 0 because you're going to end up with 3 minus 3 over 25, which is 0 divided by 25, which is 0. This is okay because we're not dividing by 0. So we want something that has what is it? That has a whole in no a 0 at x is equal to at x is equal to 3, which both of these terms do also in fact have. So once again, we can't eliminate anything. So that brings us down to our last case of a horizontal asymptote at y is equal to 1. Now for that, in order for you to have a horizontal asymptote when y is equal to 1, you need to make sure that the power or the degree of your numerator is equal to, or no, let me write it out. Let's go back to what you would need to look for in order to have a horizontal asymptote. So in order to have a horizontal asymptote, the highest power of your numerator has to be less than or equal to the highest power of your denominator. And in order to have a horizontal asymptote at a specific point on the y-axis, n has to be exactly equal to d. Otherwise, in this case, when n is less than d, the y-asymptote is just going to be at, no, not the y-asymptote, the horizontal asymptote is just going to be at y is equal to 0, or the x-axis. This is what we want. This can give us like some sort of other, like, I don't know, I'll just call it custom. In the n equals d case, that will give us a more specific asymptote, which in this case, the target is y is equal to 1. I know for a fact that every single one, and basically what's going to happen is, in this case, your horizontal asymptote is going to be the ratio between the leading coefficients of each of your terms. So you can see here that each of these has a 1 here. So I'll just write these out. So the leading coefficient for each of these fractions is going to be 1 because it's just 1 divided by 1. So every single one of these would have a horizontal asymptote at y is equal to 1, assuming that the other conditions that I listed are met. But I know right away that one of these is going to meet the conditions and one of them isn't. And the one that isn't is going to be answer choice E. The reason why is because I mentioned that the highest power being important. In this case, everything's been factored out, so in order to determine the highest power, you just have to add up like all of the exponents of each of the stuff you have in parentheses. So you can see here we have an x minus 1 to the first power and an x minus 1 to an x minus 3 to the second power here. So if you add these together, the total power of the numerator is going to be 3. But you could also see down here in the denominator, it's also 3, because we have a 1 here, 1 here, 1 here. 1 plus 1 plus 1 is 3. But in E, we only have 2 terms in the numerator, so the overall power of the numerator is going to be 2. But we want 3 because down here it's 3. So 2 doesn't equal 3. So the horizontal asymptote would be at y is equal to 0. Whereas in this case, the total power is 3, just like the denominator. So the asymptote is going to be at y is equal to 1. So yeah, so the answer to this question would be A.